Hi everyone, this is Anurag, one of the co-founders at TrueFoundry, and this week we have Vigith with us. Vigith is the principal engineer at Intuit for the AI Ops platform. I think everyone knows Intuit, like people are familiar with TurboTax and QuickBooks, which is used widely. So Vigith, welcome to the talk with us. It is a pleasure to have you here.
Thank you. Nice talking to you.
Uh, Yeah, it will be great, Vijit, if you can maybe share a little bit about what you look after at Intuit in terms of what are the areas you cover for the context of the audience, and it'll be also great to maybe share a little bit about your KubeCon presentation that your team is planning and so on. Yeah.
Sure, thank you for having me on the show. And so let me start with what we do, right? So we solve a very niche problem called observability and analytics at Intuit, and our main charter is to among few charters, the one main charter is to reduce mean time to detection and mean time to resolve, right? And that includes how it is different is that to solve this problem we went about and built something like an operational data lake, which is very different from the customer data lake. We collect data which is not PIA, of course, because it's operational in nature, but we collect data at real time, and we have to detect it in real time within a tolerance of 1 minute, less than a minute, because unless we detect, we cannot resolve. And every minute we delay in detecting causes some impact or a bad experience to the user, right? So this is the area we work on, and I lead.
Awesome.
Um,
Yes.
the key thing about this is that we get events from lot of systems, right? Not like Intuit is a big system, and we collect information from every layer of the runtime system, which includes, for example, let's say you go to TurboTax and you see a snack screen while doing an interaction. Let's say you are trying to do an operation, right? You're trying to log in, for example, or you're trying to see your W2 upload status, whatnot, right? We, if you see a snack screen, we come to know about it in real time, and then we had to detect this problem and create an alert or an incident based on the severity of the problem. This
Got
means
it.
it has to be very high throughput, because we just not limit to such data. We also collect runtime, CPU usage resource node. We are very Kubernetes heavy, meaning we have around 250 clusters with millions of pods running, right? And so we also collect this information from operational systems, and then we analyze this data at a latency of less than a minute. So the way we play this is little different from traditional customer oriented ML, because of the throughput we deal with and the low latency we have to provide.
Awesome, awesome. That's great to kind of give the audience some context. What will be great, what will be nice, Vijit, is if you can share a little bit about some of the ML use cases, right? Like maybe some that are more customer related and some that are more operational related, so that it gives a sense to how these two problems differ for the users, right?
So usually customer data like use cases, there are a lot of ML on there. I have few to start with: fraud detection, right? Even users try to steal accounts and things like that, or then scanning documents, forecasting, then type ahead things, meaning when people are typing in real time, right? They could detect whether the number you are entered is does not
Right.
match the reality, right? It could be off by a zero, meaning it has very different meaning. And then document search, like Intuit has a lot of documents. So there are many use cases, and there is a big org that supports
Got
customer
it.
problems. So hence that is, there is a customer data lake associated with that and everything. We on the
Got
other
it.
side work on very pure, non-PIA, anonymized set of metrics that give that can detect user problems or platform problems, and then
Got it.
so that is the two area. Yeah.
Got it. Understood. So that's great. Would love to know, like, you mentioned about 250 Kubernetes clusters. That's a massive scale. To kind of give users a perspective of how that translates into the number of probably, queries that comes to the system, or the number of team members at Intuit that are working on the ML. It'll be good if you can share that, Vijit,
On the
that
operation,
people get a
yeah,
sense
sure,
of.
sure. So on the operational side, we inject like I believe on a typical day at least, right? Meaning when I say typical, our systems, for example, TurboTax, there is a small window when there is a very high load. I'm not going to quote those numbers; those are very high. Okay, on a very typical day, right? We at least get a billion events just to
Wow.
analyze and process, right? To give a prediction on whether this is an anomalous event or not, right? And this includes events from resources, CPU, security. See, the whole point is, right, we didn't just solve AOps only for observability. We also can detect, we do have runtime information about CVEs, meaning which container has which images running, because we need zero-day vulnerability solutions and so forth. So the fundamental thing is an operational data lake, which can ingest data at real time, which is well cataloged and schematized, right? So in a traditional system, what you see is you see silos of data, logs siloed by metrics, which then there are traces. All of these are siloed, and each team operates differently on their set of data. What we did is we schematized the entire system and gave an unified approach to this. That way, only we can analyze data at scale. So the fundamental rule is we follow the data mesh principle. We actually, just to
Okay.
give a background, I was with Yahoo, where the Hadoop was born. I worked on that team, right? And I before this, I used to work at Hadoop at Intuit too. So we solve this problem as more of a data problem rather than observability problem or so on.
Got it.
But the use cases are operational in nature, but the tools we use internally are very data heavy, have cutting edge data technologies. We cannot solve this using siloed technologies that can actually, because at scale we need high end data solutions.
Got it. And here, like when you like that's a massive scale, like 1 billion. Maybe what will be nice, Vijay, would be good to hear about the platform in terms of how the platform is built, starting from the training side to maybe the serving layer. Like what is the architecture and what are the different challenges at each layer?
Okay, fair, fair,
Yeah,
fair. That's a very good question, and the answer will be, I think, little more interesting from the traditional way of doing it. Okay,
right.
I'll tell you how it happens. Since this happens at real time, right? What we do is the input is a unbounded stream. So usually in traditional ML, what you see is you have a request response kind of saying that you have a payload, you get a prediction or something back, right? Here, what we have is an asynchronous system which
Got it.
ingests massive amount of data, and at the tail of the system, you get the anomaly score out or a number out. In other words, we see the system, the platform is what we say it is any time series data that has a dimension or a metric could have an anomaly score.
Got
Okay,
it.
so now we have generalized the problem into that statement. Okay, now how do we do this? Is we have this is why we build Numa approach. Right, Numa approach is a platform that has set of ML models or tools, ML models we have, which we have vetted it out based on our. We have been at this for like 3 4 years. Okay, meaning we have a very stable system that can detect, and we learned a lot of things by building this. And then we thought, okay, we have to generalize this problem, and we thought, okay, there are a lot of people out there, the community who would like to get this out, right? So that's the reason we open sourced it. We rebuilt it with a lot of generalization and brought it under the tag of Numa approach. So there are two parts to it. One is Numa logic, that is a set of model which we are very confident about, which we use every day, and a pipeline
Got it.
and a platform that could actually run this Numa flow. Okay.
Got it.
What Numa Flow does is it's a directed acyclic graph based pipeline where you have between a source and a sink. Meaning source is
Hmm.
where you get the data. It could be a Kafka, any unbounded stream, Kafka, HTTP. So you can even have an HTTP endpoint as a source. And then you have
Got it.
multiple vertices where you could do for a typical design will be like you get the data, then you transform. because some data is of data of different formats. Some of them are protobuf, some of them are pure JSON. So there's a translation layer that translates based on the requirement. Okay, and it is language agnostic. That's another thing that we wanted to make sure that the problem, we need to decouple the real logic from the system we are processing, right? So it's connected
Got it.
by, so it's a direct cyclic graph with many vertices. Each vertices could be of different language. One of those vertices is of, usually we go with this pre-process, inference, and post-process. The what
Okay.
pre-processing does is it does featureization and things like that. Inference
Got it.
does the inference, and then
Right.
post-processing is something where we normalize it to a human understandable format. So think about it. At Intuit, we normalize every alert between a value between 0 to 10, no matter what,
Okay.
whether it is a CPU alert or an interaction alert, where when you click
Right.
through, or a service has more errors. Everything, everybody at Intuit knows what 4 means, right? So the way
Right.
0 to 3 is okay. Between 3 to 5 to 6 means you are deviating from the normal pattern. Your application is
Right.
anomalous, and above 6 meaning it is totally deviant, right? So
Right.
this is where we translate our scores back to a human understanding. Because if I were to say 42 for one and 103 for another, right, people won't be able to relate it to it. So then, so this is a very high level overview. The what Numa Flow provides is the guarantee about moving the message from the source all the way to sync, immaterially of whatever happens on your runtime. Because in a Kubernetes system, ports get rescheduled, there is
Right.
node migration, pod migrations, also things like auto scaling, right? Sometimes in the night time, or you don't get much traffic for TurboTax because most of the most presence is in US, right? So we need to auto
Right.
scale it down, and we need a system that can auto scale down.
Right.
If you think purely from a services perspective, you use HPA and things like that. But this is a very different beast of problem altogether, because what you're talking about is an unbounded stream, so you cannot predict
Mhm.
what's going to happen. So what we do is we calculate things like using little load to figure out whether what is the rate to happen, and we compute what should be the required number of set of processing units we need, so we can actually auto scale all the way to 0. So if you don't
Okay.
get traffic, we will go all the way. The moment we get it, we can scale up back. Meaning there are pipelines
Got it.
that get 5,000 TPS in a minute. That's it for an hour. So they use NumaFlow because very cost efficient. The moment you get traffic, we scale up, and then we do the
Okay.
processing and then scale down to 0. Right. So it's very cost efficient, and for an operational system, it's very important to be cost efficient, because the analytics we are doing is to detect a problem which we pray does not happen. Meaning nobody wants an incident. So we cannot run a very expensive system always on for an outcome that has a negative intent, right? So
Right.
the point is it has to be very cost efficient, and so this is what NumaFlow brings in. It's a real-time streaming based on direct acyclic graph, written to make the life of ML engineers easy when they do real-time data analytics.
Got it. And there's like the data scientists who are doing this data analytics work. There are hundreds of numbers. So when they are kind of doing this, for like training something like which can be later on used in production, how is the resource management and how is the training pipeline for them look like?
So the ML engineers for AIOps is very few. You can count it in
Okay,
hands. It's not a big number, right?
it's not a
It's
big
not a
number.
big number. And the way we do is we have. So the first question is training, right? So in our old system, we what we do is we use Argo Workflow to train it. All our
Okay,
training is based on Argo Workflow. So think about it. Now let me come back to the tricks, the trivia's about the streaming system, right? When you are doing at this
right.
scale, how do you even detect, how do you even configure a system to know about a new service that is coming up or a new interaction that is coming up? You cannot,
Mhm.
because that is reactive. So if a developer has to come and change the configuration for a new anomaly detection, that won't work, because people are going to
Right.
miss the whole point of this. Is they should self learn, right? So what happens is, the way it happens is, as we get data, we try to see whether we have a model. There could be three things: you have a model, well and good. Another case is you have a stale model, which is okay,
Okay.
right? And third thing is we have no model, because this is a new interaction that just got deployed. right? And there's a cold start problem, which I'm not getting into those things now. But the whole point
Right.
is, let's assume that there is enough data. We do a cotton. This is not the right word, but I'm going to say something like an inline training. What it means is
Mhm.
NumaFlow can, so it bifurcates based on, because it's a DAG, you can make decisions at each vertex and do things and
Got it.
and delegate the work to different vertices. So this is very different from any streaming system you will see, because our intent is very different. So there's a concept called conditional forwarding, where you can, okay, I do not, for example, let's say you have a scale model, it will give result to one to post process, to other it will go, say, go retrain. That is again a UDF, that a vertex that runs, retrains, updates our model store. Now when the same message comes, it will be able to pick it up, the new trained model. If it is, if no model exists, it goes to a high priority queue using again
Got
the
it.
condition forwarding, so that it will recreate, and the RTT will be lower. So that is, we do inline training. And for complex ones which takes a while, we use Argo Workflows, but most of the cases it's a UDF that runs. This is possible because in NumaFlow each message processing can have a varied distribution of time. Usually in a stream processing system, the rule is that each message should be processed in and around the same distribution. We could have some messages taking like microseconds, some message could be in minutes. We are okay with it, because you can consider NumaFlow also as an eventing system, where each message is can be independently processed with different variables, latencies. So you can use it like a work queue also.
Okay, got it. And you mentioned about like the the scaling on based on real time and scaling down to zero. Like how is the architecture of that system done to be able to scale down to zero?
So the way we
Let's say.
architect is that the processing, the scheduling logic is decoupled from the data processing logic. Okay, so we
Okay.
have a custom CRD, which is a Kubernetes controller, which is deployed. So we have a pipeline CRD, a pipeline spec, which internally creates a vertex CRD and so forth and so forth. And so it has an auto scaling where rule we have, logic we have inbuilt into the system, where we understand the rate of, what is the processing rate of a vertex, and what is the time taken to process a message. We have a distribution of that. Based on that, since we have the it's a CRD, so we have
Yeah.
the controller for that on how to do it. Hence, it's very different from a services which uses native Kubernetes HPA. We do not use
Right.
do
Right.
that. We have our own inbuilt auto scaling algorithm, because this is if you see the native ones, you cannot actually auto scale to zero, but this can
Right. Right.
let you auto
Exactly.
scale all the way to zero.
Right.
And
Okay. Amazing.
also another thing is, right, as I told, the this is a streaming system. It's a connected streaming system, right? So data moves forward, back pressure moves backward, right? Back pressure is the same thing in the fluid dynamics, right? You get a back pressure, it starts clogging up all the way back. So based on the buffer between two
Mhm.
vertices, we can auto scale independently each vertex,
Okay.
right? Because if you
Got
think
it.
about it, reading from Kafka is a very low latency, very efficient process. 10,000 metrics can be read using two, at the most, two ports, right?
Okay.
But the inference is a complex thing. It has different kind of CPU requirements and everything, right? So your consumer will be slower than your producer if you were to go with same number of resources everywhere. So to avoid that, we can auto scale independently each vertex. So you will see an architecture
Okay.
where a deployment, where the pipeline where you have two ports followed by 10 ports. And the training might
Okay.
be even more, because training needs to access way more data. So training ports could be like, we have seen the cases like hundreds running at some time when there is a new service getting on board and things like that.
Got it. Got it. Very interesting. Yeah, like the scaling down to zero has been something like we hear some of the customers needing, but
Yeah,
I
that's
think as you
our
mentioned,
one of the coolest feature is the ability to scale down to zero, and it's a must for us. It's,
okay, very interesting. Nice. This is great to know. One question, Vijit, is you mentioned about Argo workflows, right? Like, and I believe like your team contributed quite a bit to the Argo workflows layer, and would love to hear about your, openness to the open source ecosystem and maybe a little bit of insights there.
So Argo was built by Intuit and open source by Intuit, and if you and it has been a massive success, right? So meaning we get a lot of ideas from different users outside, right, which help us innovate, and we solve not just our problem; it's a community's problem we are solving by their contributions too. So that's the reason we in Numa project when we started doing this problem, we thought this is not a problem unique to us. This is a
Right,
problem that is with many people outside, and the moment we open source it we get feedbacks on, and in fact we added features based on requests from users outside of United States, right? Like or right so they'll say that hey, and then it will be an eye opener, because when you are looking at a problem and solving for Intuit, you have a lot of intuitism built into your solution, right? No matter how hard you try to make it generic, right?
right,
But the moment you open source it, it opens up a different kind of ideas that could flow in, which improves our solutions too. There are like brilliant ideas that have come in and that have improved the way we think about the problem too. So, and these are like uh, problems everybody faces. It's not a very unique problem, or so that is why we made it open source first, and we are very open to work with the community to improve the experience for
awesome.
everyone.
One question here with regards to, a lot of companies continue to use like Airflow as a DAG orchestrator, and then companies that are doing more ML workloads, I'm seeing like they are also using a lot of Argo workflows.
Yeah.
Would love to understand like your point of view as to where these two systems like differ, and which systems are more suited for
Okay.
like Argo.
Yeah, so very good question actually. So when Argo Workflow was built, there was a question in
Right.
the community saying that Argo Workflow is excellent for training. Okay, no question. We
Okay.
love it. Even we use it. Okay, it's not like we don't. Intuit uses Argo Workflow very heavily. All of the lot of batch processing systems is scheduled by Argo Workflow. The users then asked, is there anything equivalent of Argo Workflow, which is streaming in nature? If so, the one way you could think about Argo workflow versus Numa flow is Argo workflow is batch, meaning every vertex in a DAG ends only after the previous condition DAG has finished. The previous vertex in the DAG has completed. That brings
Right.
in a lot of port churns and things like that. A port startup time will be in seconds. Think about it where your none of the vertices is terminated. It's always on because there is a constant stream of data coming in. Now you could imagine both merging together as the always on is an inference system, while the batch system is a training system. So
Right.
that is one way, one analogy, because the Numa flows, there was a lot of push on streaming Argo workflow, and we even started something called Argo data flow. Actually, if you see there is something called old Argo data flow, then we
Okay.
re-architected the entire system to be much more than just streaming. Is just streaming Argo flow. We wanted to add much more to it, so we re-architected the system and brought it as Numa flow.
Okay, very interesting. And Vijit, like we were talking earlier, and you mentioned that the serving system for the operational AI ops platform is very different. Again, probably because of the same conditions around latency and the traffic being very different in pattern. Would love to hear a little
Yeah.
bit around that.
So the way it happens is right. I think I might use some artistic license on serving here, which might which might not be the contemporary serving terminology. The way we look into is when you get a data, right? How do you call a model and give the data out, right? So when it is a real-time streaming system, yeah, the inference is like any other UDF, user-defined function, right? So what we do is it follows the same architecture for any UDF, immaterial of whether you are doing protobuf to some other data conversion or inference. It all looks the same. The way we ask the user to say, give us a, we have given a NumoFlow has something called SDKs for different language. Python is the most complex of all because at a high throughput Python acts a little weird. So we have to have async IO, multi-process Python, and also the procedural Python. For other languages we don't have this problem, right? Because Python users come from different world with different use cases. So our Python library is little more horizontally more capable than the rest. So what happens is the user does not know, or the model owner or the engineer does not know how the model is going to be called. All they do is they'll say, okay, they'll write a function called a handler that will say, given a message, what would you do? That's all they care about. So they're given a message, and the NumaFlow has the guarantee has the semantics to provide the message and get the message back. So they write a handler function which has a semantic something like key comma value, and its output is a flat map. You could have 0, 1, or many results. For in a ML system, it is just one result. Okay, so you get an input, you get an output. So they're right. So I'll come to the model store and everything in a second, but the semantic is something like that. You get an input, that's the function signature. You implement the signature, you can put anything inside that function. Okay, so that's the reason the same signature applies to any vertex, no matter what you're doing. Now, coming back
Okay.
to model specific, from a model engineer,
Hmm.
what they do is when they get the model, they pull the model, they cache it based on the problem statement itself. Like some of them are heavy models, some are low rate. So they get a message, they do some XYZ, and then they return the inference, which we get it and push it to the next vertex. Now, the way that message comes in is that's very specific to our use case. Is like we do some ML flow in some high throughput, very heavily deployed, decentralized architecture. We just have a we manage our own ML with model versioning, and we have an abstraction on top of that, because we cannot put ML flow on like 250 clusters for very high throughput. Maintainability and everything is a problem. So we do everything in clusters, so the network latency and everything is way limited. Sorry, way minimal, right? So we have like
Right.
code annotations to make sure that we can really access it very fast and in milliseconds, right? Very like single digit, like 1 millisecond ish, right? But for other systems, we have an abstraction that has three level of reference pointing. For example, we put a reference in DynamoDB to S3 when the architecture is centralized, and we could play around in different times. But if it is decentralized, deployed everywhere, it is decentralized. So we choose our solution on how we store the model and do it based on the use case. But in general, the from an ML engineer, they get a message, they return a message. That's how they look into it. And they get to write, everybody writes the same handler. And it happens over gRPC, which is very not heard of also. Usually people do Rust here, but we do it over
Right.
gRPC.
Oh, nice. Yeah, we also had to implement gRPC for one of the customers, so
Yeah.
can totally understand that. One question, like, where is the model store residing? Like,
So model,
how?
so if you use ML flow, then we use ML flow to do all the management lifecycle and everything.
Okay.
But if you manage ourselves, then we have to use our own deserialize and model serialization techniques and things like that. So in
Okay.
right,
So you use a combination of both, is
we
it?
use many combinations based on the problem statement. The key
Okay.
thing is, right, when you are really decentralized, we cannot go heavy with ML flow, which requires a database, blob store, and whatnot. And then we also can play around with respect to how fast is the training in case the model store gets, it can go really purely as a caching layer with the key value cache, where we do serialize, like if you have to use PyTorch and serializations using of those, right? We even choose what kind of serialization we need to put. Like so it's very contextual. It's very contextual and based on the problem, but it's all abstracted out. For an ML engineer, it doesn't take a, it's just changing the class abstraction is so neat that they just need to change the class name and it all works.
Okay. Got it. And from a perspective of an ML engineer, right? Like, what does the workflow look like? Like, how do they kind of provision resources?
Yeah,
Like,
yeah, that's a very good question.
uh,
Very good question. So, yeah, I'll talk about resources, and I think I cut you off. So I'll let you. I'll come back to the follow-up question. Okay. So the way the resources are allocated is, um, since it auto scales, right?
right.
So they just need to give a rough approximation of a single computation requirement.
Got
For
it.
example, if there, so to make it, so one could, there's a latency versus throughput problem, right? To reduce the latency, one could say I process only one message at a time. But
Hmm.
to improve the throughput, they could do a batch. Since we have a lot of messages flowing to the system, for us batching is easier. Is will increase the throughput. Hence, it falls back on the Numa flow to give the right allocation strategy on scaling and everything. So that makes their life very. They don't like they give us rough numbers saying that oh this model mostly will take one CPU for GB of memory.
I see.
And then we can optimize based like NumaFlow at runtime knows okay this can take way more, so they will it won't auto scale. They just and if they so we don't scale unless there's a back pressure developed. So even if they give us a big configuration, say, oh, I need 5 GB, sorry, 15 GB with three CPUs, and if they have
Hmm.
do most of the time there is no backtrack, we will increase that, right? And we see that okay, this guy can take way more than that, right?
Okay.
And so that's where the auto scaling comes back and helps the ML engineers to give us rough estimates, and we will scale. Only is if they give us totally off numbers and if the quota allocated for the namespace is low, those are like that's the
Right.
only place it might run into. We hardly see those.
Right, right, right. And what is the architecture like in terms of like say from a Kubernetes cluster to the namespaces to teams and to individual researcher? Like how does that flow? Like
So each they do mostly all the ML engineering on the laptop, meaning usual way, right? Or they can use Jupyter Notebook or other set of tools. Then we will they will deploy the artifact is a container image, and this image is the runtime execution of the inference vertex, right? And
okay,
so usually, let's say we are solving a problem called uh, failed customer interaction, meaning when somebody has a problem with respect to users interacting with the website, right? That whole project can easily sit in one namespace, right?
okay,
Because of the data locality and whatnot and whatnot. So
okay,
right, so that namespace, this there will be like 2 3 pipelines running. It could share resources if they need be the model store,
got
right, and things like
got
that.
it.
So
Okay, so basically, from a problem statement perspective, like similar kind of problem statement reside or a single problem statement basically belongs to one namespace, and then there can be multiple pipelines corresponding to
yeah.
that problem
And another
statement that
thing
can be run.
is one key thing to note is how is NumaFlow controller deployed. So Numa,
Right.
we give the complete ownership to each team. So NumaFlow
Okay.
controller is not deployed at the cluster level, rather it is deployed at the namespace level. Because we
Okay.
iterate very fast in NumaFlow. Like we have releases like very often, and we are still not to be frank 1.08. Even though our API is stable with the RC release 0.8, this meaning getting everybody upgraded is a humongous. It's like boiling the ocean task. So we want to iterate
Right.
fast, and people can adopt what features they want because we are still in. We get still a great lot of ideas. So we implement, but API is mostly stable because we use the data model API, which is used for streaming. That data model is the inherent data model which we use with some additions, right? So our model won't change much. When I say data model, the pipeline data, the data movement model, right, with the streaming watermarks and some complexities associated, that won't change. But people will
Okay.
ask for some new ideas, and then we might have the APIs tweaked a little bit here and there, right? And
Got it.
users can adopt if they want that feature. So we have this. So we have a minimal CRD deployed at the cluster level, and we have the
I see.
other CRD deployed at the namespace scope. So users can
Nice space.
that gives us total freedom to iterate on NumaFlow at a different velocity, and ML engineers can
Oh,
change it. Most of the cases they
very nice.
adopt it fast, but it gives us the luxury to go ahead fast.
Right. Okay. So, one question here is with regards to like the ML
Mm.
engineers, like deploying on the namespaces. So, like the team generally consists of people who understand data science, but they also understand the engineering aspect. So it's not like just a data scientist, right? Like because,
Yeah.
uh,
So the key thing is the contract is very simple, right? You give us an image where you implement a function. That's it. That image we have a very standardized way to write an image, and everybody at
okay,
Intuit knows because Intuit is very into containerization Kubernetes from right from a little while ago, right? So For them, you write a container, you push the image. That's all you need to do, right? Where it get deployed, what's the scale is going to be deployed, all taken care of to the platform at runtime, based on the throughput of the incoming system, incoming unbounded source, right? So
Right.
it makes their life very easy. They don't have to think two times about, oh man, this is a new thing we have to learn. All they give is the container.
Right. And then going back into the retraining part, right? Like, how is the retraining system powered? Like, and you mentioned earlier, like, that's a very different kind of a system
Yeah,
as
so
compared to now.
retraining usually, so if it is, it depends on use case to use case. Some use cases we use a fully, so we batch, like say, we even the retraining will have around 20 requests per second because of the amount of data
Hmm.
and the amount of deviations that happens with respect to the system. Training is always on, right? And some of them are complex. So we deploy a full blown Argo workflow which has multi
Okay.
steps to do, multi fetch from here, do gather whatnot and whatnot, right? And then in the end, update the model store. If it is a lightweight system, we just use the same UDF because all we need to do is write a function that does what you want to do. So we don't care what it really does, and it can take different. That's the main point is that amount of time taken for a function to execute for a given input can vary. We do not have any limitation. If you look into things like Flink, the watermarks and other things get moved, or the barriers actually get moved along with the data. We do not do that. We do an out of band data watermark movement with respect to data. This help us have a different set of our constraints are not the same as that Flink has. But Flink can do like billion messages per second. We cannot do that. But our requirement is not that either.
Okay. Maybe just double click on this point. Like, what is the, say, constraints at which Flink operates on versus what your platform operates on that makes the entire architecture different? Like,
Yeah, so
that.
Flink is we use Flink as a pure data processing system where it's
Got it.
all number crunching.
Yeah.
Right? The input to Flink could be 200 kbps. So it does some number crunching and aggregates, filters, and gives to us. NumFlow's input is like 10 kbps.
Right.
Right. So in a minute, I think the highest throughput is around 10K, and it can take around 1 GB ish as the bytes per second, right? And but the problem we solve at NumaFlow is very different. It's very heavy with respect to the number crunching IO intensive activities. In Flink, if you do that, the whole thing will go. It's very tricky to get it right because you have to do, especially if you were to abstract using Apache Beam, it even get it was very complex for us. Right, the bundling and everything. The RPC, if you try to do a slow RPC on a Flink system, the whole system will backlog, and that's the reason we wanted to do this, right? The
Right.
rule number one was we want to decouple the processing speed of a message, and it can be at any latency. We do not care. So downside is we lose the flexibility of higher semantics, like very high throughput with. And second thing is Flink has its own serialization format. We do not care about for us value is a black box. That also puts that has pros and cons. Pros are like the input could be a protobuf. The third vertex might be outputting in again in protobuf or JSON, whatever. We don't care, right? But in Flink, it's all a data serialization based on Java, Python, or Go. I think they support this. That gives some very efficient way of storing messages and things like that because it's into the so their hash code equals to are well defined. For us we cannot do hash codes or equal to because for us the message is a black box. We cannot inspect and say okay, comparing two values is practically impossible unless a user writes something to help us do that because we do not the object serialization is totally on the user space, user code space.
Nice. Got it. And in this entire system, like, curious to understand how does the security come into the play? What are the things you have implemented from a security standpoint, or say from a compliance standpoint, especially with respect to the kind of platforms Intuit runs, right? Like,
Oh,
so curious.
Intuit is very, very strict with security, meaning we even have our own encryption, application level encryption algorithms, which is very proprietary to Intuit. But On the AIF side, I can talk more on the AIF side because the other one is way complex because of the because
Okay.
it has sensitive data too, right? But ours is
Right. Right.
our data classification is not as strict as theirs is because we do not have any PIA data whatsoever. Anything even
Right.
close to it, right? In fact, if the worst thing will be the IP address. So, right, but it doesn't. Everything on rest and in transit is encrypted whatsoever, even with all those, meaning even though so it's totally isolated, each names, that's the reason the controller is also namespace related also for another reason.
In specific.
It is each namespace is like a watertight compartment, and each word,
Got
any data at rest or in transit is encrypted with TLS. Right. On rest we encrypt it using some other kind of encryptions, but anything on transit is TLS. Even though there is just a vertex to vertex sitting, it could be the same pod in the same node. Still, it is encrypted. I'll tell you why is like is because from the learnings we had from Argo, right? When you make a open source project, security is a big thing. So we
right.
want to make sure that we follow the same security principles Argo has,
Okay.
right? So for us, even the metrics endpoint, just to see the metrics of a pod is encrypted. So you cannot do port forward and symmetric. It's an encrypted
Okay.
endpoint, right? So our encryption is all the layer, and we use Argos semantics for that because it is pen trusted and everything. It's a big project under CNCF. It's a graduated project,
Right.
so we have a lot of learnings from that, right? So it makes our life easy with us when you work on the second project.
I'm guessing like the customer MLOps, like that would have even tighter security constraints, right? Like in terms of
Yeah, it
uh,
is way more, way more. Right? There is a next level security. Meaning, yeah, the key thing is even users cannot see the data that easily,
right.
right? It's well audited, well kept because it has to, right? It is very secure system. That's the reason we decoupled. Now, if you were to type back, that's the reason we decoupled operational data from customer data, like because
Very
the
interesting.
amount of complexity of that systems are very higher, and right, but for the operational data we don't really have to be that strict because the data classification is under lower, the sensitivity is way less,
Right. Right. Right.
but it
Got
does
it.
not mean we
So
can be loose either, but so
right.
we
Right.
follow on Argo security principles, Argo approaches.
Understood. Understood. Maybe for the folks listening, it'll be good to summarize the major principles at which like the ML ops versus the AI ops part differ, right? Like from your perspective, like which basically lead to like different decisions that people need to make. So it'll be great to hear from you on.
Yeah, so from the AI's point, one key thing is we use a lot of like so both are good, like AOps is mostly on the operational domain itself, while MLOps,
Right.
just to make sure that we both are saying something, right? MLOps is more about the model life cycle, model tuning, right? So let me talk about the AOps. The thing is that we use a lot like things like hyperlog log, which has a error percentage of 0.89 percentage, right? Which is totally possible with operational data, right? But
Hmm.
we cannot use with the customer data. So secondly, we use as like latency is based on sketches, Apache data sketches, which also can have some approximations built into it. It need not be 100% accurate. We are okay if it is like 99ish, because the sample point or the data should be statistically significant. That's the key thing in operational domain. It should be statistically significant to detect the problem is, and it should be enough to keep isolating to the next level, so that you can get closer to MTTR, right? On the MLOps side, we do like we use different technologies based on the, like for example, in some cases we manage the life cycle of a model ourselves
Hmm.
based on last trained, and we can even revert a model based on some heuristics we have. Right,
Yeah.
at runtime, we do those things. But in some cases, we use ML flow and things like that to manage it. In some other cases, we do it using the patterns which have been done at Intuit. For example, there's something called feature management. So that's quite. I don't want to get into it because that's more on the customer side, customer data
Yeah.
like side. But our most of our our solution is on AI ops, that
Got it.
make the life of a DevOps engineer easy to detect a
Right.
problem and resolve the problem.
Perfect. Amazing. I think Vijit, great chatting with you. And this is like generally when we talk to companies, like we talk more on the MLOps platform, which is like generic customer side problems. Like I think the way you all have built the AI ops side of the platform is quite different, and it will be a really nice and a new perspective for a lot of people listening in. So that's great. One last thing I wanted to kind of hear from you is maybe on the LinkedIn. I saw about the presentations you are giving at KubeCon. So maybe just a teaser for people as to what people might expect to see as it kind of gets published, and what you're planning to cover.
Yeah, unfortunately, we couldn't fly to Europe. We were supposed to be there for the Europe presentation, but it is more about customer centric AIOps. What it means is it's not system centric versus customer, meaning we are alerting based on customer's experience rather than system centric. So, for example, we do not alert when the CPU goes up. That is a derivable information. There is always we do have the insights there. You come to our, you'll see that in the demo, in the talk itself. Actually, once it comes out, you'll see. So what happens is we see one thing about is not about detection. Detection we are quite good. We do it in under a minute, but ability to isolate. So we build complex dependency graphs based on tracing data. Like our tracing system gets like 2 million spans per second, 2 to 3 million. So you can imagine how much data that goes through. And based on this has context too. So we know who called who. If and we can use some transitive relationships to really build the entire graph. Now we can give anomaly scores or the state of your application at each vertex. So saying that hey, this application is bad. We could even be very specific and say this application has 10 clients. Of that, only one link is anomalous. We call it service to service anomaly. So
Right.
the way the AIOps is done is defined in one simple principle that your data is a collection of dimensions and metrics. Now, you can do anomaly detection on using composite keys. What that really means is you say, I want dimension X, Y, and Z and do anomaly on metric M1, M2, and M3. Now, with this power, you can do any kind of anomaly detection on a time series data and you can give any level of insights. The only thing that the limiting factor of this is when you go too low into these dimensions, right, the cardinality increases and the data will become sparse, right? Then the sparsity problem will kick in. So let's say I want to do at the region, comma, state, comma, county level, right? Then there will be only one user
Right.
using once in 1 hour. You cannot do any anomaly detection, meaning, right? But if you remove the county and come to state, there are users happening every minute, right? That way we can even pinpoint anomaly to at very specific level, right? I mean, so that is how we see this AI. We do not say it is, oh, we need service and this. It just two dimensions from the point, right? So it's a very generalized system. They just literally have to say x comma y metric m1 comma m2. That's it. So and the aim of this project is to do anomaly detection by yourself. We call it do it yourself anomaly.
Okay.
So without generalizing it into metrics, comma dimensions with the time as a
Mhm.
time in the x-axis, it cannot be a generalized solution. It will be always a very specific solution. So that's why we build this platform so that we can generalize it. And all our use cases at Intuit for IAOs runs on this platform because of the generalization of the simple thing.
Right. Awesome. That's great. We'll look forward to the talk. I mean, last thing for the users, like anything like you'd recommend people to kind of, good resources on ML engineering side or in general engineering side. If people are looking to build these platforms, anything that you'd recommend maybe.
So, top of mind, I cannot think of any resources per se. But one thing I would say is there is much more into streaming these days. You'll
Okay.
see the trend changing. Earlier, it was all about batch, like it's okay. But now it is
Right.
low latency, detect as soon as possible and as lightweight as possible. Right? The time taken to detect is very, very important. So that's the streaming has a much more. and ability to use, easy to use. The learning curve is also like with streaming is not like batch, because batch you don't care about time, actually time, because you are given a set of data. In streaming, time is everything, because you cannot define anything without having it, adding the word in X minutes or something. Otherwise, the data it's in. If I were to count the number of balls going through in a pipe, I cannot count it. I don't know the answer unless you tell me per 5 minute, per 1 minute. But in a batch, you are given a bucket full of balls. You just need to count dump the balls down from the bucket and just count it out. So that time dimension is very, very important. And in streaming, you will see that playing very radically different role in processing altogether.
Awesome. Thanks, Vijit, for the insights. Like, it was great. I think there are a lot of topics that can be further deep dived into, and I hope that there will be more content from Intuit to learn for the users. But really appreciate the
Thank
time
you.
you
Thank you
spent.
for
Thank you for
for having me on the show. It was really nice talking to you.